So good afternoon, everybody. Thanks for inviting me. It's a pleasure to be here today for the first time at the Karlsruhe Dialogues. So, as mentioned, my name is Umberto, and I'm a research lead at the Sensible City Lab at MIT. So I would like to start with this picture. So this is a drawing by the 19th century. Back there, street light was carried out by oil or gas, and people would actually go there and light it. So the figure of the lamplighter was a big public job. Well, nowadays things are a little bit different. So those are cities around the world. Lights are not switched on by people, but by computers. These computers are able to see when it's dark in the city, and with that, they can switch all the city on. So in an engineering term, this is what we call a feedback loop. So there's a part of sensing, a sensor, a physical device, a physical electronic device sensing some information. But also what is important is that there's another part, an actuating, an action that is being taken and have a consequence on the city. So this is made possible by technology. So we all know that computers run the world, but back in the last century, this was a computer. Mainframes were huge as this room, and then what happened? The size decreased and decreased. So computational power went up, so from personal computer went to laptops. Now the computational power that brought the man to the moon in 1969, we have it now in our pocket or around our wrist. So everything is going smaller and smaller. What's the limit? So some people call it the smart dust. So sensors as tiny as grain of rice that are basically everywhere. So everywhere around us, we have these loops of sensing and actuating. And this is the concept of smart dust. Not only because now objects are not just electrified and intelligent or defined so, but they are connected. So we're going through the Internet of Things, objects communicating not just to people but to other objects, and everything is now connected in our cities. So where are we in all this complicated world? So we are basically in the middle. So there's a physical layer, the things we touch, the people we see, the world we used to know before, and all the digital traces we leave behind. Whenever we use a credit card, we make a phone call, we use public transportation with a contactless card. So all these digital traces form a new layer of our cities. Where are we? We are right in the middle. Is there a layer more important than another? No. Those are equally important. The real challenge today is try to recombine them and use the digital layer to understand and plan better the physical layer, which are ultimately our cities. So let me explain and show you some of the projects we do at Sensible City Lab. And I would like to start with this one back in 2006 in Rome. So some people might remember it, and Italian gets very excited from this. This was the year of the World Cup, and Italy won the World Cup. So we developed this project in partnership with Google and some telecommunication companies in Rome. We could track people and see all their cell phone activities. So when people would make a call or send an SMS. And we could geolocalize it, and so we could see where this happened into the city. So as you can see here, there's the city of Rome, there's the Colosseum, the river. So this was the day before the match. People here and there, you see some cell phone activity. People talking to the city center. So this before the match. Then, at one point, the match began. Silence, complete silence into the city. Italy scores, France scores, halftime, people make a short call. End of the time, Zidane's headbutt in a minute, and then, boom, Italy wins. People very excited, people celebrating. Then people would move into the city center, celebrate more, spend all the night celebrating. This is the night, and in a moment you will see the following day people celebrating a lot. So today, this doesn't astonish us. This is not rocket science today, right? Back then, it was the first time that we could see at people and cities dynamic through data. Taking one step further, we wanted to try and understand not just people dynamics, but also objects dynamics. And you can do this with data. So for example, take this computer. We know each component of the computer, where it comes from, where it has been produced. This is the map of all the supply chain. So the geographical point where each of the chip was produced. Very little we know what happens when I throw away this computer. So very little we know about the second life of objects, the trash. We can refer to it as the removal chain. So we don't have data for this, right? We don't care about things we throw away. So we had to build a physical chip. It's like a smart tag. It tells where the object is. We engineered it in our lab, and then we asked people to bring us their trash. We attached this smart tag to the trash, and we told them, go home, throw this away as you normally would. So we deployed this in Seattle. Yes. So in 2009. So 500 people came, and here you can see some of the objects they brought. Everything. Bagel, banana peel, phone, cell phone, really everything. And then we started looking at the data produced. So out of 3,000 objects thrown away in the city of Seattle, this after a couple of days, things were starting to move. After a week, they crossed the national borders. 2 weeks, 3 weeks, you can see the United States of America here. After a month, after 2 months, still objects moving around. So we understood 3 good things from this. So the first one is that nobody had seen this before. There were not data for this. It was the first time that this picture appeared. You can start making some calculations, because you see that the system is very inefficient, right? So you can start making some calculations on why these objects went in this place, and why something went from Seattle to Chicago and then back to California, and something straight to California. That's not the real point. The real point is that we could know which object was what. So we discovered that it's not the banana peel, the problem. We know how to dispose of a banana peel. The objects that traveled the most were the electronic waste. Of course, it's new technology. We don't know how to deal with it. The third very good thing we discovered is that a lot of things that would go into some port cities, they would stop there, and the signal completely stopped emitting. So we redid the experiment just with electronic waste. We concentrated on e-waste, and with international SIM cards, so that people could, so that we could track this internationally. And this is the result. So things basically were sent away into the Far East, into different countries. And we know this is illegal for electronic waste in the US. We could actually go and see and track these objects, went to all these countries, and this is what we found. The good thing about this is that people reacted. A lot of people said, now that I know where my wastes go, I stopped buying plastic bottles, for example. I start using water bottles instead. So this is how we like to do research. Yes, deploying certain technology, developing some technology, but also not just writing scientific paper, showing to the people with the language of design, with videos, with visualizations, what we discover. Sometimes we don't need to design physical sensors because data are already there. Take this car, for example. This is a normal car, the one you would find out on the street. There are more than 2,000 sensors in a car. They're recording temperature inside or outside. Whenever you use the window, you switch on the lights. What can we do with this data? These data are constantly being recorded, and so there's a very good information about not just the car itself, but about the people who are driving cars and the surrounding environment. So for example, we know when people brake. We can then use this information for classifying roads in terms of safety. So even if an accident doesn't happen, but some people broke and had a very harsh event, we can point it on the map, and looking at different people at a city scale, we can see where are the dangerous roads, for example. We can study how people drive. So we know that people drive differently, right? We can tell on a scientific base who is driving better. We can use this data for better and more fair insurance, for example, or for teaching people to drive actually in a better way. So speaking about car, we all know that huge research efforts are put into autonomous driving. This is real. It's not the future. There are already some cars, autonomous cars, in the road. The real question here is not how the car will change, but how the city will change. So probably there will be a fewer number of cars into the road, because the same car that brings me to the office today can go back to my house and give a lift to any other member of the family, and then go into the city and give a lift to anybody else in the city, for example. This is what a self-driving car sees. This is basically what LiDAR technology allows. So it's a laser scanner on the top of the car, looking around, tracing objects. With this technology, the car will know the position of each of the other cars in the street. So a question could be how the streets will change, how the intersections will change. If we think about it, intersection is a point of conflict in the road. How do we solve today this conflict? Traffic light. In the future, probably traffic lights are not more being used. Why? Because each car will know where other cars will be. And so a collective intelligence can optimize these fluxes. So we try to visualize this. And let me start the video. So on the left-hand side, there's a normal intersection with traffic lights. On the right-hand side, these cars going all the directions without apparent order. But actually it works. And if we look at the waiting time, the average waiting time, and if we look at the emissions, everything is much better optimized. So this, I think, should trigger a discussion, because people start asking, so where are the pedestrians? Are people ready for this? So those are all good questions that the research should trigger in people. So moving on, sometimes the right question to answer is not self-driving cars. Take the city of Amsterdam, for example. There are more canals than streets. So probably the best question here would be, can we develop self-driving boats? So putting together two different words and deploying something new. So we try to prototype them. We call them rowboat, because after all, they are robotic boats. And what can they do? They can bring people around. So we started to prototype them in-house. So we had to add some different sensors, from different thrusters to the technology that is able to see around. And this is what the robot will see. So it's a 3D scan of the city, of the canal, and different alternatives for getting this track. This is a deploy we did last week in Japan. of the first prototype. In orange, here you can see the trajectory, and despite of the waves in the water, this boat can go around and follow the trajectory. But probably, again, the most interesting question here is, what can it bring to the city? Which type of services? How the city will change? So, of course, this technology can carry around people, but also goods, for example. We like to think of it as a sensing platform, as a platform that senses the city and answers questions, like, what's the quality of the water? What's the quality of the air? Where is my delivery, for example? The good thing about this is that they can act together and bring life to new infrastructure or new services in the city. For example, this is a market. Instead of having vans driving into the city and moving, this platform can assemble together and give a new space for people in the city. We can try to solve some city problems. We went actually in Amsterdam and we saw that trash collection was a big problem because there's no space in the streets. So why don't people can just throw the trash in these robots in the canal? Or we can leverage the existing infrastructures. So for example, this is a normal water taxi. In the future, without changing disruptively the technology, we can bring life to it and make it self-driving, just tagging it with a robotic boat. Or in case of an emergency, in case of a big event in the city, these different platforms can assemble together and form a temporary bridge to make people move in a faster way. So those are just examples. I would like to stop here because the good thing that this research should bring to the discussion is not the technology itself, but how this technology could help different cities in the world. So we know that every city is different. So people should really start thinking how this technology could improve my city. What are the problems of my city that can be addressed by this technology? And hopefully, not looking at the technology just as a scaring future, but visualizing it and picturing, simulating how it will work, we can ask people, do you like it? Would you like to change it? What are the problems that you will be happy to solve with this? Thank you very much.